The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Let's get started. Couple of announcements. Reminder about the periodic table test, which will be added next week on the 23rd. You can see the website if you want to download a copy of this to practice on it. You're required only to put the 1 or 2 letter chemical abbreviation, the symbol. Some people asked me if I wanted you to know the molecular weights and so on, and I thought that was a bit excessive. So I think if you just know the symbols for the ones that are up there, that'd be just dandy. Here's the lady's scarf. Very hot, black. See, trim lines in blue and gold, and it's got elements on it. Very hot, very hot. There's a necktie, comparable fabric, comparable pattern. It's not geeky. This is very hot. You need this. You need this. Okay, let's get on with the lesson. Last day we looked at Rutherford, Geiger, Marsden, and the experiment that they conducted on the gold foil, and out of that came the recognition that Thomson's plum pudding model is not sustainable in the light of this evidence, and instead Rutherford proposed something akin to a planetary system. And there's something I'd like you to be tuned into here. Now, people to this day are looking for a theory of everything. And there was something very appealing about the notion that the rules that govern the motion of heavenly bodies might be applicable down at atomic dimensions. So this is very, cosmic, There's a gestalt here. So we ended the day with Bohr's model of the atom, which derived from the conceptualization of Rutherford. And this model is quantitative. And I think I put up the postulates. And what I'm going to do today is go in some detail through the Bohr model. So let's do that. So I'm going to put up the most primitive version. It's a 1-electron atom. So it's got a nucleus at the center, charged positively. This is where most of the mass resides and the positive charge resides. And orbiting around this is a lone electron out at some distance r. And I don't have to worry about these relative dimensions because we know from Marsden's calculations that on the length scale that I've shown here, these would be just tiny little dots. It's about 10,000 to 1, the ratio of the nuclear dimension to the entire atomic dimension. And so we have a positive charge in the nucleus, which is given by the number of protons. So this would be a 1-electron atom. It could be hydrogen, it could be helium plus, it could be lithium double plus, and so on. These are all 1-electron atoms, and they're gas. It's gas, a single atom. So this will be Z times the elementary charge. Remember, E represents the elementary charge, not the charge on the electron. The charge on the electron is minus E. So this is Z times E in the center. And out here we have the charge on the electron as simply equal to E. So I'm going to highlight this by calling this Q1, lowercase q being the charge here on the nucleus, and lowercase q sub 2 is the charge on the electron, and that is given by minus E. Minus E. And so the other thing that we consider is the nucleus as being stationary. So we have an orbiting electron but a stationary nucleus. And Rutherford, whom I've already described to you as being a little bit colorful in his language, he backed up Bohr on this, and he says, when an elephant has fleas, it's the fleas that do the jumping. So that's why we don't worry about the motion of the nucleus, because the ratio of masses is about 2,000 to 1. So what I'm going to do is use these postulates and go through the basis for the Bohr model. The first thing we're going to do is describe the energy of the system. So the total energy of the system, which we're going to get from postulate number 4, which says the energy of the electron, which is the energy of the system, is the sum of the kinetic and the potential energy. So let's write that. And as I've reminded you at the end of last day, the only reason I'm doing this for you right now is I want to elucidate the principles. It's not because I favor derivations in class. I've been teaching long enough to know that doing derivations in class is equivalent to pouring ice water on the proceedings. So I do this sparingly. So it's a Newtonian system from the mechanical standpoint. So this is going to be a half mv squared, where this is the mass of the electron. And then the potential energy, the energy is stored here due to the Coulombic force of attraction between the electron and the nucleus. So in the most general form, Coulomb's law is the product of the charges Q1, Q2, divided by their separation, which is R. And in order to rationalize electrostatic units with mechanical units, we have to put a factor in here. Otherwise, the units that come out of this calculation won't dovetail with the units that come out of this calculation. And that factor is 4 pi times epsilon 0. Epsilon 0 is the permittivity of vacuum. And now we can plug in Q1 and Q2. We know that we've got half mv squared. And then Q1 is plus QE, Q2 is minus E, so then that will give us a net minus Z times the square of the elementary charge over 4 pi epsilon 0 R. And I'm going to label this as equation 1. And so this is a mechanical term, if you like, mechanical. And this is electrostatic or Coulombic. I'm going to use different words for that. And where do we find these things? We can find values of all of these if you look at your table of constants. If you look at your table of constants, this is the table of constants in its entirety. But if you look up really close, there's the elementary charge E. There's the mass of the electron. All of these are given here. This is 9.11 times 10 to the minus 31 kilograms. This is 1.6 times 10 to the minus 19 coulombs. There's the permittivity of vacuum. It's all up there. Okay, so you have these at your disposal. So now let's do the next step, which is a force balance. That comes out of postulate 3. Out of postulate 3, it says Newtonian mechanics applicable. So let's put a force balance. So I'm going to say if that electron is to stay in its orbit, that is to say it doesn't flee the atom, it doesn't collapse into the nucleus, then the sum of the forces on the electron must be 0. No net force. No net force. And so that'll be the sum of a dynamic force plus a electrostatic, or just to be pluralistic in our language, Coulombic force. And so you know from your Newtonian mechanics, as you're learning in 801, the dynamic force here is mv squared over r. Again, m is the mass of the electron. And now the force in its most general term is Q1, Q2 over 4 pi epsilon 0, which is the conversion factor, r squared. Force goes as 1 over r squared. Energy goes as 1 over r. And if you ever get confused, the way to remember these is that you know that energy is the integral of a force moving through a distance, right? Energy is the integral of force moving through a distance, so the integral of 1 over r squared gives you 1 over r. If you get them backwards, you'll integrate 1 over r, you'll get log r. That makes no sense. So there we are. And we plug in our values, and we end up with mv squared over r minus ze squared over 4 pi epsilon 0 r squared. And I'm going to call this equation 2. So that's our force balance. And then for the next piece of information, I'm going to go to postulate number 5. And postulate number 5 is some of Bohr's early genius. Bohr says that the energy is quantized through its angular momentum. He's talking about the energy of an electron. No one until this time had suggested that a system would be subjected to quantization except for light. Planck had already enunciated back in 1900 this E equals h nu. In other words, that the photon has a quantum of energy h nu. So quantization of radiation was already established as of about 1900. But no one dared say, we've got this little planetary model, I've got an electron orbiting a central nucleus, and I'm going to endow that electron with quantized states. That was a big leap, and that was Bohr in postulate 5. So postulate 5, I'm just going to reproduce. So that's mvr, which is its angular momentum, does not take continuous values. It takes discrete values, multiples of some integer n, and the multiplication factor is the ratio of the Planck constant divided by 2 pi, where n takes 1, 2, 3, and so on. And I'm going to call this one equation 3. So I've got 3 equations and 3 unknowns, and I'm not going to take the time to solve it because I think that's a waste of class time. But those are the 3 unknowns: the radius of the orbit, the energy of the system, and the velocity of the electron. So I'm just going to present you the solutions. Let's look first of all at the radius of the orbit. If you solve for r, you'll end up with this. This is the permittivity of vacuum, square of the Planck constant times pi, mass of the electron. I'm going to stop putting subscript e. It's the mass of the electron times the square of the elementary charge times n squared over z. Z is the proton number of protons in the nucleus. So what do I see? I see that r takes on discrete values. R is a function of n, takes on discrete values, and in fact, the functionality is that of the square of this number times a constant, So this tells us that the radius of the electron orbit, first of all, there is more than one radius. There's a plurality of values. Secondly, that those values are discrete, they're quantized. And third, it's nonlinear. So if I look at something that goes as n squared, if this is the edge of the nucleus here, and if this is R1, it says when n goes to 2, the radius goes to 4. So this is, let's say this is R1, this is R2, and then this will be R3, and this will be R4, and even that's not to scale. Okay, so the higher the n number, the greater the radius by far. And this applies to all one-electron atoms. All one-electron atoms. So let's look at the simplest case. Suppose we look at elemental hydrogen. So in the case of elemental hydrogen, Z will equal 1. And then let's look at the lowest orbit, N equals 1. That's the electron in its lowest orbit to the nucleus of atomic hydrogen. And this lowest orbit is termed the ground state. The ground state. First floor. So if we put 1 here and 1 here, the value is simply given by this constant. And if you evaluate the constant, you get that R1 is equal to 5.29 times 10 to the minus 11 meters, or 0.529 angstroms. I like the angstrom. It's 10 to the minus 10 meters. It's not an SI unit because it's not a multiple of 10 to the third, but I like the angstrom. I don't like the nanometer. I like the angstrom because atomic dimensions are conveniently measured by angstroms. And this is given a special symbol, A0. A0. It's the value of the radius of the ground state electron orbit in atomic hydrogen, and this quantity is termed the Bohr radius. And you don't even have to look it up because it too is given on your table of constant. There's the Planck constant, it's number 5. There's the Bohr radius down there, number 24. So you just look that up, and you know anything else is going to be some multiple of it. The other thing I'd like to draw your attention to is this, that I can simplify this in the following manner. Say that Rn, now that I've got a Bohr radius for this bracketed quantity, I can write that as the product of the Bohr radius for the value of the orbit in any one electron atom, specify the quantum number n, divide by z. So that's this rewritten in a much more compact notation because you have the value of this. And note that as z increases, as the proton number increases, the radius decreases for a given n number. So if you look at the ground state in 2 different systems, if you look at the ground state, which is n equals 1, think about this. If I increase the proton charge, the Coulombic force of attraction is greater, and so therefore, all other things being equal, the first orbit should be at a smaller distance. So this is making physical sense. Okay, now let's look at energy. Let's quantify the energy value. If you go through and solve for energy, you'll get this equation. E is equal to minus mass of the electron times the elementary charge raised to the 4th power divided by E times the square of the permittivity of vacuum times the square of the Planck constant times Z squared over N squared. So again, we see that E is a function of N. You see, the quantum condition, by putting quantization into the angular momentum, it's propagated through the entire system. Orbit's dimensions are quantized. Energy is quantized. Velocity is quantized. Everything is quantized. So energy is quantized. It has a different N dependence. If I lump all of this together in some constant, I can then represent that formula as minus k times z squared over n squared, where n again chooses integer values, 1, 2, 3, and so on. And we can go through and calculate the value of this quantity in parentheses, and when we do so, we get the value 2.18 times 10 to the minus 18 joules. This is 10 to the minus 18 joules for this one atom. So I'm going to draw attention to this. It's joules per atom. Right? Or if you multiply by Avogadro's number, then you'll get joules per mole. And if you do so, you'll end up with 1.312 megajoules per mole for this quantity K. And you can find that one too. That's on your chart. If you multiply entry 23, which is 13.6 electron volts, I'll show you what the electron volt is in a few minutes, so we'll just put it up here prematurely. But that's given in your chart. And then the conversion of joules to electron volts is entry 42. So if you multiply those two together, you'll end up with this quantity. And so let's take a look at what that does in terms of graphical representation. I tried to give you a simple graphical representation of, so that was Cartesian space, right? When I plot R as a distance out from the nucleus, that's sort of our simple-minded planetary model. So now let's look at energy. So energy, I'm going to put energy in the following manner. See, it's a conservative system, so all the energies are negative, right? That quantity in parentheses, I've got a mass, which is a positive number. Something raised to the 4th power has got to be positive. Something raised to the 2nd power, it's got to be positive. So everything inside the parenthesis is positive, so minus a positive number. All the energies are negative because it's a bound system. So I start up here with n equals 1, and over here, this is the value of minus k. And then if we go to n equals 2, what happens? We go to n equals 2 for a fixed value of z. Let's make this z equals 1. We'll do it for atomic hydrogen. So it's k over 4. And then we go to n equals 3. This is not to scale, but and so on. So this is what the energy level diagram looks like. This is for atomic hydrogen gas, and I'm going to put on here not to scale. There's some relative, the notion that the energy gap between n equals 1 and n equals 2 is greater than that for n equals 2 to n equals 3. That's correctly represented. These are definitely not equally spaced, but they should be even more disproportionate than I've shown it. And finally, up here we have n equals infinity. When n equals infinity, R equals infinity, and so the energy is 0 because the electron is no longer bound. It's free. The electron has been liberated. This represents the free electron. It's no longer tethered to the nucleus. So there's no energy stored in the system. And the closer it gets to the nucleus, the greater the amount of energy, which means that you see this in the following manner. This is called the ground state, n equals 1. I already mentioned that. It's like the ground floor. I know some of you come from Europe and other parts of the world where they have the ground floor is rez-de-chaussée or some silly thing like this, and you push the button on the elevator to 1 and you go up to the first floor. You are in America now, and the international chemical community calls the ground state n equals 1, not n equals 0. So please observe the traditions of the International Union of Pure and Applied Chemistry, not to mention Niels Bohr. Okay. So this is ground state. These are the excited states. These are the excited states. And free electron at n equals infinity. And at this point, we say that the atom has become ionized. Ionized. That is to say, the electron has been ejected. And so now we have net charge. And we can calculate the ionization energy. The ionization energy must then be nothing more than, that's the energy to go from the ground state here, from the ground state to n equals infinity. So that would be the energy at state infinity minus the energy of the ground state. Well, the energy at infinity is 0, and the energy in the ground state is minus k. So minus k is plus k. So k, in fact, is the ionization energy. And in fact, if you go to the chart, to your periodic table, indeed, there it is. So here, this is a slightly different version from the one you have, but it's the same order. If you look on the periodic table, this is atomic hydrogen, and sure enough, there's 13.598, which is this number here in electron volts. That's the ground state energy of atomic hydrogen. The other thing to note is look at the dependence upon Z. Suppose instead of hydrogen, we considered lithium plus, lithium 2 plus. Lithium 2 plus is a 1 electron atom. Lithium has 3 electrons. If it loses 2, 1 remains. What is this formula telling us? It's telling us that the ground state in lithium would be Z squared. It would be 9 times more intense. It'd be 9 times less. That is to say, minus 9 is less than minus 1. Okay? And that makes sense too, because the positive 3 pulling on minus 1 has a tighter binding energy than positive 1 pulling on minus 1. So this drops by the square, whereas you saw how the orbit goes. So just picking up on this ionization energy, the ionization energy we can define as this is the minimum energy. This is the minimum energy to remove an electron, from the ground state, take out that ambiguity, of an atom in the gas phase. All the things we're talking about here are with reference to the gas phase single atom. So we don't have to deal with work function or any kind of energies associated with some condensed form of matter. So we're really looking at this reaction here for ionization. It's H gas neutral goes to H plus in the gas phase plus the electron. Okay? And furthermore, we can have multiple ionization energies. If you have multiple electrons, we can lose them in sequence. So for example, I could look at the ionization of lithium. Again, lithium gas. Lithium gas loses an electron to become lithium ion plus electron. I can then subsequently lose an electron from the lithium ion. So lithium ion loses an electron to become lithium 2 plus. And then lithium 2 plus still has an electron. Let's denude lithium 2 plus. So lithium 2 plus loses its electron to become just this is the analogy to the alpha particle, right? This is the alpha particle with the helium nucleus. This is the lithium nucleus plus electron. So we call these first, second, third ionization energies in sequence, right? This is the first ionization energy. This is the second ionization energy. That is to say, the ionization energy of the second most electron. And this is the third ionization energy. Now, where do we find these values? Well, if we look on the chart, the first ionization energy is what is reported in your periodic table. So the first ionization energy of lithium is about 5.4 electron volts per atom. So we can get this from the periodic table. Okay, reported in periodic table. And this is determined by measurement. This is determined by measurement. This one here can't do anything for you. Have to look that one up. What about this one? This one is calculable by the Bohr model because lithium 2+ is a 1-electron system. So I just go through these equations, but be careful to put in Z equals 3, and I can calculate this from Bohr model. Bohr model, let's say calculable. Calculable by Bohr model, and then remember Z equals 3. So showing some versatility here. And let's see, we've talked about radius, we've talked about energy. Let's talk about velocity, just for completeness. So the velocity is given by this product of the quantum number n, Planck constant, 2 pi, mass of the electron, times the radius of the orbit, which itself is a function of n. We can make some substitutions here using some of the derivation on the previous board, which will give us the Planck constant divided by 2 pi, mass of the electron, times the Bohr radius. All of this times the ratio of Z over n, where n equals 1, 2, 3, so on. And we rarely look at velocity because we don't, as you'll learn very quickly in 3091, we're going to abandon this strict adherence to a planetary model pretty soon. But it is interesting. Let's just, for an order of magnitude, say what happens for ground state electron and atomic hydrogen. So we're going to put atomic hydrogen Z equals 1, ground state n equals 1. That's just this quantity here. So let's find out. So V1 in atomic hydrogen. Is it fast? Is it slow? What's the number? Plug in the values. You get 2.18 times 10 to the minus, 10 to the plus 6 meters per second. 10 to the plus 6 meters per second, which is about 1% of the value of the speed of light. 1% of the value of speed of light. By the way, C, the value of speed of light, in case you can't remember it, is the number 1 entry in your table of constants. So 1% of speed of light. So I would say that's relatively fast. That's a pun there. Think about this as a relatively fast. Okay. Well, yeah, this is. You people have no sense of humor, no sense of joy, no sense of joie de vivre. You're so young. You've only been here a week and so jaded. You got 4 years to go. So where does C come from? How come the speed of light has the symbol C? Where's the symbol C? It comes from the Latin word celeritas, which means swiftness. We get the English word accelerate from the same root word. That's why we have one. So we have C. All right, so we're in pretty good shape here. We've got a Bohr model. Bohr model's quantitative, so it makes predictions that can be tested. We've got energies. We've got radii. So is there any experimental evidence that can put this to the test? And the answer is yes. In the early 1850s, Ångström up at the University of Uppsala in Sweden was conducting experiments on atomic hydrogen. He was doing experiments in a gas discharge tube. He had a tube with electrodes potted in it, filled with atomic hydrogen, and by applying a voltage, he was able to get the gas to glow. And then he analyzed the components of that radiation. And this is what he found. First of all, let's take a look at his experiment. There it is. He used the prism spectrograph to analyze his results. So what do we have here? Here's the gas discharge tube. This is the diagram taken right from your text. There's the 2 electrodes coming in, and this is atomic hydrogen in the gas tube. And so if he gets the voltage high enough, this gas discharge tube will glow. And the light will be going in all directions, obviously. It's a glass tube. So he wants to narrow the light, so he puts a couple of slits here, and then he just takes that narrow column of light and he admits it to a prism. And what the prism does is it takes a tiny, tiny difference in wavelength and refracts it through a different angle. And if the prism is of sufficient dimension, that angle can be magnified. And then further, you put some recording device, which in those days was a photographic plate, far across a room. So you take a tiny, tiny angle, and you go far enough across the room, and now you get separation on the order of centimeters. And we record here. And this is the blow-up of what's on that photographic plate. And this was painstaking work, okay? What you've got here is the photographic plate demonstrating a spread. First of all, that the glow is made up of constituents. There are distinct lines here. What appears to the naked eye to be just glowing is actually superposition of different lines of distinct frequency. So you see, this is quantized. It's quantized. And so he published his results around 1853, and so they lay. So let's get 1853. Let's get Ångström up on the board here, since he did the work. He was Uppsala in Sweden. So he measured the line spectra. Line spectra of atomic hydrogen. By the way, your text has a glaring error. The label above this figure refers to H2. Take the fattest marking pen you have, scratch that out, and replace it with atomic hydrogen. You do not get this line from hydrogen, molecular hydrogen. So we've got the line spectra lying out there in the literature, and people read the literature. They read. And one of the people that was reading this literature was a school teacher, a high school teacher, who was teaching mathematics in Basel, in Switzerland. So this man he also had the initials J.J., as in J.J. Thomson. This is J.J. Balmer. And J.J. Balmer, in 1885, playing with the numbers associated with the lines there. You notice how the lines are colored? Your book isn't colored. See, I colored them for you. You know, I care about you. I wanted to illustrate that these are representing different wavelengths in the visible, you know, and the doctor told me it's good for me to express my creative urges, because it's so I got out my pen and I did that. Where was I? Oh, so what Balmer did, all he has is those four numbers. He's got the wavelengths of those four numbers, and he's playing with those numbers. He's determined to make sense of those four numbers in some kind of a sequence. And this is what he came up with finally. He came up with the relationship that nu bar, which is called wave number, which he found the reciprocal. What he did, he coined this, but he found that by taking the reciprocal of the wavelengths, you've got four numbers, he took the reciprocals of those wavelengths, he found that they fit a sequence, a numerical sequence. 1 over 2 squared minus 1 over n squared, where n takes values 3, 4, 5, 6. 3, 4, 5, 6. And there's a constant out here, and the constant, if we redo it in modern SI units, would take on the value of 1.1 times 10 to the 7th reciprocal meters. 1.1 times 10 to the 7th reciprocal meters. So how does this support the Bohr model? Well, in order to answer that question, I've got to give you a little more background information. First thing I'll do is give you the understanding of what's the physics of the gas discharge tube. So let's take a look inside that tube. So let me redraw it. I'm going to redraw it horizontally. So this is a glass tube. There are some feed-throughs here to allow electrodes to be potted. So these are gas-tight feed-throughs. And these electrodes are then connected to a variable voltage power supply, and it's possible to change the voltage on the plates. And the way I've got this configured, the left electrode is going to be charged negatively, and the right electrode is going to be charged positively. So this will be, the left electrode will be the cathode as I've configured it, and the right electron, the right electrode will be the anode. And what is inside the gas discharge tube is gas at low pressure. Gas at low pressure. As we increase the voltage, we get to a critical value at which it's possible to actually draw electrons across the gap. Electrons will actually boil off the cathode and accelerate across. You've got a positive electrode here, and the electron is charged negatively. It will be drawn to the positive electrode. So it will accelerate from rest, crash into the anode. So if we have nothing here, we see nothing. If we have too much gas in here, in other words, if the gas is at too high a pressure, the collisions with the gas molecules will consume the energy of the electrons, and again, we'll see nothing. So if we get the pressure in there just right, we'll allow for gas-electron collisions, and then we get the glow that ultimately was sent through the slits. So that's the operation of the gas discharge tube. Now let's look at the physics. What's the energy of the electron? The energy of this electron accelerating from rest and crashing into the anode here. Well, it's going to be mechanical, a half mv squared. And how about potential energy? It's not bound. It's a free electron, so there's no potential energy to be accounted for. So it's simply half mv squared. But I can equate the amount of energy, mechanical energy in the electron, to the amount of electrical energy that was imparted through the electrodes. And the electrical energy is the product of the charge on the electrodes, the charge on the electron times the voltage, which is the potential difference through which the electron was accelerated. And so this allows me to, by increasing the voltage, increase the energy on the electron. So you can see low voltage, low energy, high voltage, high energy. It's a linear function. And how about order of magnitude? Let's see. Suppose I took, let's do everything unit. That's a good way. Let's say, suppose I took, what's the unit charge? The smallest charge I could put here would be 1.6 times 10 to the minus 19 coulombs. And what if I took a unit charge and I multiplied it times unit voltage, 1 volt? Unit charge times unit voltage then would give me what? If I multiply these two, well, what's the coulomb times a volt? You see, here's the value of using SI units. SI units means everything goes in SI, everything comes out in SI. What's the energy unit in SI? The joule. What is the unit of charge in SI? Coulomb. What's the unit of potential difference? Volt. With impunity. With impunity, if I use coulombs here and volts here, I don't even think. I write 1 times 1.6. Even I can do that in my head. That's 1.6 times 10 to the minus 19. And I write joules. That's the power of having a rationalized system of units. So that's the good news. The bad news is I hate this number. Look at 1.6 times 10 to the minus 18. We got 2.18 times 10, 1.6 times 10 to the minus 19. 2.18 times 10 to the minus 18. Yap, 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 yap. Can't we get simple numbers like 3, 7? Whatever happened to good old numbers? So I have an idea. Why don't we define a new unit of energy that is nearer to what we have to measure? And that was done. So what people did is they said, let's define a unit of energy that represents a unit charge accelerated across a unit potential difference, and let's call that the electron volt. That's 1 electron volt. The electron volt is not a unit of potential difference, it's a unit of energy. So now, this is 1 eV, so now you can see 2.18 times 10 to the minus 18 joules can be 13.6 EV. Now, I don't have to, fill my head with 2.18 times 10 to the minus 18, 13.6. That's a cool number. I can remember that. All right, so that's how that works. By the way, this is the cathode, and we have a beam. It's an electron beam. The electron beam. In the 1890s, the latter part of the 19th century, a very fashionable word was ray, because it came from optics, the rays of sunlight and so on. And in fact, even when we first started pulling synthetic fiber, the first synthetic fiber, cellulose, was referred to as rayon because it looked like a ray that was being pulled. So this, rather than calling this an electron beam, this was called a cathode ray. This was called a cathode ray, and this is a tube at low pressure, and if I evacuate it, I have a cathode ray tube. And in fact, instead of having just an electrode here, what I could do is I could have an electrode that's hollow, and then I could put a flat end here, and I could put phosphors here, and then I could put a couple of plates, and I could raster the beam so that when I'm looking here, the beam goes back and forth about 80 times a second, and the phosphors glow, and I can be watching science documentary. All right, and the other thing I have to teach you is matter-energy interaction so that we can see how the Balmer series validates the Bohr model. So there's one more thing you need to know, and I'm going to put up this energy level diagram again. So this is infinity. Let's call this 3, 2, 1. So this is E1, ground state, E2, E3, and so on. And this is 0. Okay, so let's look at the energetics of one of those electrons crashing into a hydrogen atom inside the gas tube. So here's an electron, and I'm going to let this arrow somehow indicate the value of the incident energy. And I'm saying electron, but more generally it applies to any incident particle. Later on, we could do this with a proton. We could do it with a neutron. We saw Rutherford used alpha particles. We could use argon ion. There's all kinds of different ways of bombarding, in this case, hydrogen gas. Now, if this incident energy is great enough, it'll take an electron out of the ground state and promote it. But the electron cannot reside anywhere except in one of these quantized states. So suppose the E incident is greater than the energy in the transition going from ground state to n equals 2. What will happen? That energy will be absorbed by the hydrogen atom. The electron will rise from n equals 1 to n equals 2, and that amount of energy will be subtracted. And then over here, this electron will continue, and I've purposely made the arrow shorter to indicate that it has been slowed, because we're going to argue its mass didn't change, so the only way to change its energy is to change its velocity. So this will be now the scattered. We'll call this, it's scattered now. It's interacted. This is the scattered particle. But it doesn't end there. So how much energy is there? If this is, let this represent the total energy of the incident electron. And if that's the energy to go from n equals 1 to n equals 2, then this is the amount of energy that's going to be left as kinetic energy of the electron. It's like an elastic collision between billiard balls. You've seen these things. But it doesn't end there, because the electron is sitting up here at n equals 2, very nervous, because there's a lower energy state, and there's a Coulombic attraction of the nucleus. So what happens, almost instantaneously after the collision? The electron up here falls back down. And when it falls back down, that energy is given off, and it's given off in the form of a photon. It's given off in the form of a photon. And what's the energy of that photon? Well, the energy of the photon, we know from Planck, is h nu, which is hc over lambda. So now I've got lambdas associated with transitions between energy levels in atomic hydrogen. Gee, I wonder if I could come up with a set of transitions occurring inside atomic hydrogen that just might match what Ångström measured back in 1853. So that's going to be the challenge. That's going to be the challenge. The interesting thing here is that I can change the incident velocity continuously, right? This is continuously variable because I can vary voltage continuously. Change the voltage, I change the incident energy. What about the energy of the emitted photons? Are they continuously variable? No, they are discrete. They're discrete, and furthermore, they're characteristic of the target gas element. So, let's say I got up late and I'm racing to get to class, and I just burst in now, and I look up there and I go, that's atomic hydrogen. Because only atomic hydrogen has that set of lines, which means I could then take the spectra of gas phase species and use that information to identify. So this is now a technique of analysis. I could take an unknown gas and put it in and measure it and then say, wow, those are the lines that are characteristic of sodium. Gee, have you ever wondered how they know the composition of stars that are light years away? Do they get sample bottles coming in? How do they get that information? What is a star if not just a giant gas bottle, containerless? It's glowing. And why is it glowing? It's glowing because electrons are excited. And they're excited and they're jumping up and down and they're emitting, but they're just not emitting anything. I mean, why are some stars this color and some stars that color? Somebody painted them that way? They're different because they got different compositions. So you could use this in order to identify the contents of stars. All of this. So, what did Bohr do? I want to tell you a couple more Bohr stories. Bohr, the guy was great. Okay, so here's what happens. Here's a story. Capstone of Bohr's work on the Balmer formula. Huh? Let me simply tell you that in time I'm going to show you that this formula is inconsistent with the Bohr model. You see that at the beginning of the next lecture. So in 1896, Charles Pickering from Harvard found a series of lines in starlight which he attributed to hydrogen, even though they did not fit Balmer. They were off by a factor of 4. Now, what do you know about energy? Already from this class, if I told you that I gave you energies in some spectrum, but they were off by a factor of 4, what would you think? It's probably, maybe the Z is wrong. So, even though the lines were wrong, he says, no, it's hydrogen. So Bohr says, no, it's not hydrogen. It's helium. That star's got ionized helium, helium plus. Z equals 2. Energy will be 4 times more intense. So Pickering was nasty SOB, and he said, you're wrong, because in fact it's 4.0016. And the 1/6 is greater than what I would have as experimental error. So your theory is wrong. So Bohr says, oh yeah? So he goes back and he redoes the calculation, only in this case he says, all right, what I'm going to do is I'm going to redo the calculation for helium, but I'm going to consider not just the mass of the electron, but the reduced mass of the system. So I'll take into account that there is some contribution of both the nucleus and the electron. And he gets, you're absolutely right, it's not 4, it's 4.00163. Take that, right? So what you have is, with a simple calculation, 5 significant figures. 5 significant figures. That shut him up. Now, to just show it doesn't end, more nonsense at Harvard. This is Cecilia Payne, first woman graduate student in astronomy, first PhD in astronomy, first woman to receive tenure at Harvard. She was awarded tenure in 1938, denied a professorship for 18 years, and when she presented her PhD thesis, she was the one that determined that the sun is made dominantly of hydrogen, not iron, the way most of the old goats thought, because the earth is made of iron. Heaven knows everything is made of the same stuff, right? All heavenly bodies, even though the sun is glowing and the earth isn't, but oh, they must be made of the same thing. And after all, we're Harvard, so we know. So here's what she did. She was fastidious. Look at this. What do you see there? Well, you see iron, but you know, this is misspelled. So you make an excuse and say, the detector isn't working. You know, this is the noisy system. So that's what everybody else is doing. But what Cecilia's doing is she's saying, I got to keep looking. I need a consistent picture. So this is what spectroscopy is. Spectroscopy is how you go and look at patterns, not just individual lines. So when she defended her thesis, she was forced to put this phrase in her thesis: the enormous abundance of hydrogen is almost certainly not real. Yeah, this is the way science welcomes newcomers. This is the way science, on some occasions, welcomes new findings. Yeah, just up the street. Yeah? And I'm not talking about, the 1600s. This was in the 30s. So this is a painting of her. Dudley Hirschbach, who's a Harvard chemistry professor who has a Nobel Prize, had this painting hung at one of the halls, and it's obviously referential to Vermeer's The Astronomer. So we've come a long way from the gas discharge tube to the heavens, but it shows you that with a little bit of understanding of quantization, you can go a long way. Okay, we'll see you Friday.